Okay, good day, math. This is Math 140, College Algebra. I'm Professor McCully, and this is the presentation for Lesson 7.5a on solving systems of linear equations in two variables. I'm breaking up this 7.5 lesson into three sections because there are a number of different systems of equations that they're trying to ask us. Today, we're going to focus on linear equations in two variables. So let's get to it. Today we're going to solve systems of linear equations in two variables graphically. We're going to use the methods, we're going to use algebraic methods to solve linear equation systems in two variables, and then we're going to use linear systems in two variables to solve problems. Here we go. So a system of linear equation is two or more linear equations that have single or multiple solutions. This portion of the lesson is only going to solve on linear equations of two variables. That's linear equations that you are most often used to. There are other types of linear equations, but we're going to be talking about, in general, y equals mx plus b, or ax plus by equal to c. And so graphically, the solution to a system of linear equations is just the point where those two lines intersect. What is a graphical solution to a system of linear equations in two variables? Since both equations are linear, they are graphically represented by lines. Thus, the solution of the system is the set of all ordered pairs that is the same for both equations. In most instances, that's only going to be one set of values. Graphically, the solution to the system is where the two lines intersect. Linear equations in two variables have only three ways that two lines can intersect. Those are one point, no points, or infinitely many points. And what do I mean by that? If a system of linear equations has one solution, then you will have two lines that intersect, and the solution to that system is this point right here. This is one solution. If you have no solutions, we are talking about parallel lines, and so that system has no solutions. And then you can have infinitely many solutions, and that will be when the system has two equations that are exactly the same. So using technology to solve systems of linear equations, and this is for our graphing calculators. So the first thing you're going to do is you're going to want to solve both equations for y, and then you're going to plug them into the calculator and find an appropriate viewing window. So the first equation will be y1, the second equation will be y2, and then we're going to find the point where they intersect. To do that, we are going to use the intersect feature to find the solution. There are two basic methods of algebraic solution, and the first one is substitution, and it's easiestly used if both of the equations are in the y equals mx plus b form, where you could set the equations equal to each other and solve for x, and then substitute x into either of the original two equations and solve for y. That's one way to do it. It's not the only way to do it. And I'll show another example here, but that's a simple way. Linear combination, elimination, or row reduction, those are three different ways to name the same thing. And it is best used when you have a system where all the equations are in ax plus by equals c form. And the way we're going to do this is we're going to multiply the equations by a scalar, so that if one of the variables in each equation has a factor of -1 difference. And I'll show what that means here in a minute. Then we're going to combine the two equations by adding, and we'll solve for the remaining variable, and then we'll use the result from C to solve for the other variable. And that's just the steps. So a couple special cases before I start doing examples. If the equations are the same, or you get 0 equal to 0, then the equations are the same and you have infinite solutions. So if they don't look the same right off the bat and you start one of these processes and you end up canceling everything out, then you know that you have infinite solutions. And then if you get an untrue statement The linear equations are parallel and there are no solutions. So what do I mean by an untrue statement? If I were to say something like 0 equals to 4, this is untrue. That's not true at all. And so if you get 0 equal to 4, something like that, 0 equal to another number, that's clearly untrue. You're going to say that they're parallel and we have no solution. All right, so first example, we're going to use technology to solve the system of linear equations. And the good news is that this one is already in y equals mx plus b form for us. And so while I am pulling up my graphing calculator here, I will solve this second one into y equals mx plus b form. So the way that I'm going to solve this is I'm going to have negative 2y equals to negative 6x plus 4. And then we'll divide both sides by negative 2. So I'll have y equals 3x, and then it'll be minus 2 when I divide 4 by negative 2. So I have two equations. This one is going to be my y1. This one here is going to be my y2. And so I'll grab my graphing calculator, hit my y equals, open this up just a little bit, hit my y equals, we'll clear out the noise from the last one. And the first equation, 2x minus 7. So 2x minus 7. And then the second equation here, let's see, I've got 3x minus 2. So 3x minus 2. Let's open this onto a standard window. So let's go zoom 6 and see what we get. And so I'm looking at this equation on my standard window, and it looks like they're going to intersect somewhere down here. All right, they're getting wider up there. So I need to move my x's over a little bit and move my y's down a little bit. So I grab my window here. I'm going to go from negative 15 now to 5. And then we'll go from, let's say, negative 20 to positive 5. And let's make the scale here 2's. And let's see what we get. And hey, there is our intersection. That's the point that we're looking for. So we're going to go second. We're going to hit the trace button. And number 5 is the intersect feature. And right there, it looks like I've got my intersection right off the bat. So we're going to hit enter. We're going to hit enter again. And hit enter the magic third time, and so our intersection is negative 5, negative 17. That is the solution, negative 5, negative 17. That is the solution to that system of linear equations. All right, next. Here we're going to solve the system of linear equations by a substitution. And so here's what I'm going to do. I'm going to take this one, and there's lots of ways to do substitution. All right, and as you go through this, you're gonna see different methods that are gonna be easier. In this case, I see that if I were to solve this thing for x, that would be the easiest way to solve this. So I'm gonna solve for x. And so what that's gonna do is that's going to give me x equals 1 minus 2y. And so here I'm going to take this new solution and I'm going to plug it into, I need a T there, into the second equation. So I will have, I'm going to take this, it's a 5, and so I'm going to replace the x with this expression here. It's going to be 1 minus 2y minus 4y equals to negative 23. Now, I have an equation that has only one variable in it, so I'm going to solve for y. All right, so if I want to solve for y, the first thing I'm going to do here is distribute. And so I'll have 5 minus 10y minus 4y equals negative 23. Let's simplify. And let's subtract 5. So negative 10 minus 4y, or negative 10y minus negative 4y will give me negative 14y, and then negative 23 minus 5 will give me negative 28. So when I divide both sides by negative 14, I'll have y equal to 2. And so divide by negative 14. And then I'm going to take this thing and plug into the x equation, which is right here. And so I'll take that and go x equals 1 minus 2 times 2. That'll give me x equal to, it'll be 1 minus 4 will be negative 3. So my final answer is going to be the ordered pair, negative 3, 2. That is my final answer for that one. All right, last example. We're going to solve the system of linear equations by elimination. So what we want to do is we want to multiply one or more of these two equations so that I get the same coefficient, and one's positive and one's negative. Now, I could multiply this top function here by negative, or by 5, and the bottom function by negative 3, and get my x's to both be 15. But if you notice this one here, I've got 2 and 4. If I only, or negative 2 and 4, if I only multiply this thing by a positive 2, then I will have a positive 4y and a negative 4y. And when I add those together, the y's will cancel out. And so I'll keep my numbers a little bit smaller by looking at the situation and coming up with a solution that's easiest for this situation. All right, so once again, I could, no problem, I could have multiplied this thing by 5, I could have multiplied this thing by 3 and negative 3, and I'll have positive 15 on the top and negative 15 on the bottom. But my numbers get really big if I do that. So I'm looking for the simplest solution, and I think the simplest solution is just to multiply this thing by 2. So 2 times 3x will give me 6x. 2 times negative 2y will give me negative 4y. And then 2 times 20, or excuse me, 2 times 12 will give me 24. All right, so when I add these things together, all right, I'm going to get 11x, and then I'm going to get 44 here. And then positive 4y and negative 4y will cancel out to be 0. And since I have a 0 there, I can go divide by 11, and 11 goes into 44 4 times. And now I can plug x into either of the originals to solve for y. So I'm going to take this and I'm just going to go back to this original equation, and I'll go 3x minus 2y equals to 12, and we'll go 3 times 4 minus 2y equals to 12. And so I get 12 minus 2y equals to 12. Negative 2y will equal to 0 when I subtract. That means y has to equal to 0. And even though we get a 0 there, that's okay, because look what happens. If I go back up to here and I go 4 for x, 5 times 4 is 20, and so 0 times 4 would be 0, so that works for both of these. So this is actually going to be, not only is this a solution to the system of equations, it ends up being the x-intercept for both of these at 4, 0 as my final. Well, that's all I got for today, folks. So the Marvel fun fact of the day, according to director James Gunn, the obscene gesture performed by Chris Pratt in Guardians of the Galaxy from 2014, I can't believe it's that old already, was completely improvised and was added to the final cut of the movie. And you can use your imagination on what the obscene gesture is, but this is a family-friendly video, so I got the censored version of the video. Have a good day, folks. Goodbye.